right, everyone, here is our last chunk of Chapter 3. This is the last section that is on Test 2. Section 3.7 is on indeterminate forms and L'Hôpital's rule. Some people write it out as hospital. The guy's name was Hôpital. He was French. So this is L'Hôpital's rule. Okay, so let's look at this limit right here. If we go to plug 1 in, natural log of 1 is 0. 1 minus 1 is 0. In the past, in other problems, we're able to look at graphs or use algebra to cancel stuff out to avoid dividing by 0. But unfortunately, we can't do that for things like this. Also for things like this. So when we have these expressions that look like 0 over 0 or infinity over infinity, these are called indeterminate forms because we cannot determine true values by algebraic means. L'Hôpital's rule says, suppose f and g are differentiable functions. That means you are able to take the derivative of both f and g, and the derivative of g does not equal 0. Now, if either of these things are true, then we can use the rule. The limit of the top and bottom both go to 0. Sorry, f and g are numerator and denominator functions, as in this expression. Or the top and bottom both go to positive or negative infinity. Then, this limit equals the limit where we have the quotient of the derivatives. So if we have a form that gives me 0 over 0 or infinity over infinity, and these can be positive or negative, then we can use L'Hôpital's rule, which says the limit of this quotient here on the left is the same by L'Hôpital's rule as the limit of the quotient of the derivatives. So we have an indeterminate form of the type 0 over 0 or of the type infinity over infinity. So let's look at some examples here. The one that we just wrote out was the limit as x goes to 1 of natural log of x over x minus 1. What I mean is that was the example that we looked at up here. So we know this is of the form 0 over 0. So first we check this guy has the indeterminate form of 0 over 0. That means we are able to apply L'Hôpital's rule. And now we just find the quotient of the derivatives. So on top we have 1 over x. On the bottom we have 1. So we have 1 over x. And now we can just substitute x equals 1, and we get 1. So for this next one here, let's check whether we have an indeterminate form. Well, e to the, as t approaches infinity, e to the t gets bigger and bigger and bigger, and so does a huge number being squared. So this is an indeterminate form of the form infinity over infinity, and so we can apply L'Hôpital's rule. So we now find the limit as t approaches infinity of the derivative of the top, which is e to the t, over the derivative of the bottom, which is 2t. Now this one is also of the form infinity over infinity. So we can actually apply L'Hopital's rule again. Now we take the derivatives again. So the top stays e to the t, the bottom stays 2. And so now we can think about what happens as e to the t continues to grow, as t grows. So this is going to get really huge. E to the really huge is really huge, divided by 2 is really huge. So we can confidently say this is going to approach infinity. Note that L'Hopital's rule can only be used for indeterminate forms, when we have 0 over 0 or infinity over infinity. We can't use it for other things. So in this case, right, as x approaches pi from the left, sine of pi is 0, and on the bottom we have cosine of pi is -1, so 1 minus, sorry, I think it'll make more sense if we just write the numbers down as I'm speaking. So this is just going to be equal to sine of pi over 1 minus cosine of pi. Sine of pi is 0, cosine of pi is -1. So we have 0 divided by 2. Oops. Oh, I think I hit the camera button there. And this is just going to be 0, right? So we don't need to use L'Hopital's rule here. We don't have an indeterminate form. We didn't have 0 over 0 or infinity over infinity. So let's look at indeterminate products. So suppose the limit as x approaches a of f of x is 0, and the limit as we approach a of g is plus or minus infinity. Then this limit is going to be 0 times plus or minus infinity. So this gives us another indeterminate form of the type 0 times plus or minus infinity. We can't just confidently say that that's going to be 0. So we can convert this indeterminate form to one of the more familiar types by writing this guy as the limit as x approaches a of f of x divided by this fraction. We're forcing this guy on the bottom. Or we can force this guy on the bottom like this. Then we can determine the limit using L'Hopital's rule. So the limit as q approaches 0 from the right of q times natural log of q. We will write this as natural log of q on the top and 1 over q on the bottom. So this is the same thing as that. We have forced it to be on the bottom by writing it as a reciprocal in the denominator. So now let's check here. So as q approaches 0, natural log of q is going to approach negative infinity. We can think about that in this way. So e to what power is going to get me closer and closer to 0? So what I need is 1 over e to some special power here, right, that will get me closer and closer to 0. Well, what that's saying is I need this to be really, really big. I need to be dividing by e to the huge to get closer and closer to 0. So that means this number up here is negative and huge. On the bottom, I have 1 over 0. On the bottom, I have 1 over 0, right? And I'm approaching 0 from the right, so I'm getting closer and closer to 0. And so this fraction right here is going to approach infinity, right? I have 1 divided by something that's shrinking and shrinking and shrinking. So 1 over tiny approaches infinity. So we now have an indeterminate form. We have confirmed that. So we can apply L'Hopital's rule. On the top, the derivative is 1 over q. On the bottom, the derivative is negative 1 over q squared. So I have 1 over q divided by negative 1 over q squared. So this is multiplied by negative q squared on the top. So this is going to be negative q. And as q approaches 0, this will get closer and closer to 0. Indeterminate differences. So let's say we have this guy going to infinity and this guy going to infinity. Then the limit of their difference is infinity minus infinity, and that is another kind of indeterminate form. So the game here is to try to convert this into an indeterminate quotient and use L'Hopital's rule. So here's an example of that. Calculate the limit as x approaches pi halves from the left of secant minus tangent. So let's look at our circle here. So we're approaching pi halves from below. That means my rotation is approaching pi halves from angle measures that are less than pi halves. Okay, so my secant here is 1 over cosine. So cosine of pi halves is 0, but as I'm getting closer and closer to pi halves, the cosine is getting smaller and smaller. And since the cosine is getting smaller and smaller, so as x approaches pi halves from the left, we get 1 over tiny, which is going to approach infinity. Similarly, the tangent, right, the slope of this ray, as we rotate, as x approaches pi halves, that slope is becoming more and more and more and more positive. So the slope is increasing. So the tangent is also approaching infinity. And so this guy is an indeterminate form of the form infinity minus infinity. So since we have a difference here, we're going to try to write that as a quotient. And the trick with trig is to rewrite everything in terms of sine and cosine. So let's just play with this for a sec. So we have 1 over cosine minus sine over cosine, which is 1 minus sine over cosine. Now we can check for our indeterminate form here. Cosine of pi halves is 0. Sine of pi halves is 1. So on the top I have 1 minus 1 gives me 0. So then here my indeterminate form is of the form 0 over 0. So since I've justified that, right, I can use L'Hopital's rule. The numerator, the derivative of that is going to be negative cosine. And on the bottom, the derivative is going to be negative sine. Those negatives will cancel. So now cosine of pi halves is 0. Sine of pi halves is 1. So we get 0. Okay, here's the tricky one. Indeterminate powers. Okay, now we're looking at the limit as x approaches some number of f of x to the power of g of x. So if both f and g go to 0, then we have an indeterminate form of the type 0 to the 0. And if they both go to infinity, then we have an indeterminate form of the type if f goes to infinity and g goes to 0, then we have a different indeterminate form of the type infinity to the 0. And here, if f goes to 1 and g goes to plus or minus infinity, then we have yet another indeterminate form of the type 1 to the infinity or negative infinity. The point is that we can't calculate what these numbers are. We cannot determine what they are. Even though anything to the power of 0 is 1, well, we don't know whether that's true when that base is 0. And we don't know whether that's true when the base is infinity, right? Like these are numbers that we can't compute. So for indeterminate powers, what we do is we use logarithmic tools. So we start right here. We take the natural log of both sides. So we have natural log of y equals natural log of the right-hand side. And we use our favorite trick, which is this exponent can come to the front. Then we find a limit for this one. And then we're able to use the continuity of natural log and raise e to this limit to get our answer. So we have y equals f to the g. So we have e to the natural log of f to the g. The g can come to the front. We figure out what this is. We're going to call this guy L. We're going to call this guy L. And the final answer will be e to that number. Okay. So let's look at this first one. Actually, I'm going to save the examples for a separate subpage. let me just skip to the summary and then I'll do the examples later. In summation, to find limits for indeterminate forms using L'Hopital's rule, we determine the indeterminate form. We convert to an indeterminate quotient if necessary, so forcing things to look like this or like that. Take the natural log of the function of interest, or raise e to the natural log of the function of interest, and then calculate the limit using L'Hopital's rule or other algebraic means. And I just want to stress that until you can get the thing to look like either one of these two indeterminate forms, then you can't use L'Hopital's rule. What I mean is, if we have these, then we can use L'Hopital's rule. Okay? There's lots of different indeterminate forms that we went over, but only until you can get your limit to look like this can you use L'Hopital's rule. So like I said, look for the other video that shows these two examples.